Okay, today we're going to start with chapter 2, section 4, nuclear stability and radioactivity. If you want to follow along the book, it's on page 34. First, we're going to define radioactivity. It's a process by which isotopes decompose. The process by which isotopes decompose or decay. Decay is another word for decomposing. Now, an isotope, remember, is an atom that has the same number of protons and electrons, but has different number of neutrons. So it's going to have a different weight. Carbon has a bunch of different forms. One that we saw in the POGIL we did was that carbon-6 has 6 protons, because it's carbon, and also has 6 neutrons. It gives it a total mass of 12. Now, there's also something called carbon-13. Carbon-13 still has 6 protons, because it's carbon, but it has 7 neutrons. So it's still carbon, but it has a different weight, and there's lots of isotopes for all of our different elements. That's why when we look on the periodic table, the atomic masses are decimals. They're actually averages of all the isotopes that exist in nature of each element. So an isotope is something that has a different number of neutrons, same protons, electrons, different number of neutrons. Because what happens is those neutrons in there are what react, or this decay. And when they break down, they give off this energy called radiation. Nuclear reactions are actually reactions that change in the atom's nucleus. And they are the ones that actually produce the radiation. That's why it's called nuclear reactions, going on in the nucleus. There are 3 types of radiation that can occur. One is called alpha, A-L-P-H-A. And it's the Greek letter alpha. They go by the lowercase Greek letter alpha. It looks kind of like a fish the way I draw it. If you use it in the symbols, off the symbols menu, go to the Greek letters. Looks almost like a little A. Beta is the second one. And that's like a funky, it's like a capital B, but it's got a funky tail on it. And the last one, the most dangerous one, is gamma. And that looks like a downward swimming fish, or an upside down Y. So these are all Greek letters. That's where they come from. It's alpha, beta, and gamma. And you read about these a little already. And I'm going to get into all the details of each and every one of them. But if we look at this picture here, it's probably easier to see on the printed out one. But up at the top, you'll see the alpha rays are way up here. Okay, they're very, very light. And they're going towards the negative. So if they're going towards a negative, it must mean that they're positively charged, because opposites attract. Now, if you look down here by the positive side of that magnet, you'll notice the beta go down there. So they're being attracted to the positive, so they must be negative. But the weirdest thing, I guess, is that the gamma are unaffected, so they don't really have much of a charge at all. We'll get into all those details. Now, almost all atoms that you encounter in everyday life have a stable nucleus. They're not radioactive. Radiation is, it should be an S, is dangerous. Okay, you've heard of radiation before, especially now with cancer being so prominent in our society. It actually kills the cancer cells, so obviously it's not good if it's killing cells. Okay, here's a little things to think about. The nucleus is made up of 2 things, and you know this. We just did this in the last section. It's made up of protons, and it's made up of neutrons. Okay? And the second thing we have to remember when we're looking at this radiation is that positive charges will repel each other, right? Likes will repel, opposites attract. So positive and negatives attract. If you have 2 positives together, they're going to want to kick each other out. So here's the real question. Why don't the protons fly apart from the nucleus? Inside the nucleus, you have all these positive charges, right? That's what Rutherford said. And he said that the electrons are floating around on the outside. So why aren't the protons repelling each other so much that they're just bursting? They're trying to kick each other out all over. Well, here's the reasons. There's a strong force that overcomes this repulsion, and it's known as a strong nuclear force. This force is extremely important. It's what keeps our world together. So the neutron does not experience any electrical repulsion because it doesn't have a charge, right? It has no charge, or it's neutral. It does, however, help in lessening the repulsion of the protons. The neutron is the glue that holds the nucleus together. So basically, if you are in a room with people you don't like, okay, let's say it's you and 5 people you do not like, and you're in this tiny little room, you're going to repel each other, right? But if you add like maybe 5 people who don't really care one way or the other, they're going to be able to get in between you and the people you don't like, and you'll be able to tolerate it. Well, that's what the neutrons are. They're hanging out, they don't have a charge, they don't really care, but they're actually kind of a cushion between all the protons, so the protons don't repel each other. So the neutrons are really the thing that are holding all of these wonderful elements together. And between hydrogen and calcium, on your periodic table, their number is 1 to 20. You'll see that the nucleus is stable because they have similar numbers of protons and neutrons. Like hydrogen has 1 and 1. Calcium is around 10 and 10. It's around 20 and 20 because it has a mass of 40. So they're about the same number of protons and neutrons. So it's like being in a crowded room and having not just you and 19 other people you don't like, but then there's 20 people in there to kind of lessen it, make everything light and nice so people don't argue. After calcium, though, protons in the nucleus need more neutrons to stay stable. As you add more and more things that want to repel each other, you're going to need more and more buffers, more and more people in there that are going to stop you from fighting. And then it gets to be just too much. After 83 protons in the nucleus, which is bismuth, there's just no number of neutrons that's going to help. Okay, there's just too many of you. So there's no number of neutrons to hold the nucleus together. And those are the ones that are going to be radioactive. Their nucleus is just not strong enough to hold together. The protons really do want to repel each other and spread out, and that's where all this energy comes from. So there are 3 types of radioactive decay. That's how decay happens. That's why. That's what's going on in the nucleus. So it's called a nuclear reaction. But this is the 3 types that we just talked about a little earlier. Remember, they were alpha, beta, and gamma. Remember, they were the alpha symbol, the beta symbol, and the gamma. And they're distinguished both by their charge, mass, and their penetrating power. I should put a comma there. Charge, comma, mass, and penetrating power, which means how deeply they can penetrate. Okay, how deeply they can go into your skin if you're hitting yourself with radiation, how deeply they can go into all different things. We'll look at alpha first, because they are actually the weakest. Okay, so this is the weakest, and we're going to go all the way down to gamma, which is the strongest. Okay, excuse me. Alpha radiation is a stream of high alpha particles, which is made of 2 protons and 2 neutrons. So it looks just like the helium ions nucleus. Okay, you saw that in the POGO. So you may see it written as, I'm just going to write it over here on the side because I don't think I can write it in there and be legible. So 4 to He. Now remember, this is your atomic mass, and this is your atomic number. So it's saying it has a mass of 4 and 2 protons, so it has 2 neutrons also. That's why it's also known as a helium ion. It can only really travel, it doesn't have much penetrating power, sorry. It doesn't go very far. It can only travel a couple centimeters. And it can be stopped by paper and clothing, so it's not that dangerous. Okay. Beta is going to get a little more dangerous. It's going to be a little stronger. It's actually a high-speed electron. It's not the electrons that come from like the outside orbitals of the atom. The electron actually comes from the nucleus. So if you're in here, you're in the nucleus itself. So what happens is one of the neutrons in here, in the nucleus, it's neutral, right? So an electron comes speeding out. It changes into an electron. The electron comes speeding out, and a proton is left inside, because a neutral means it's got positive and negative charges. You look at it that way. So the positive part stays in the nucleus, but the electron gets sped out. And this electron that speeds out, that's actually your beta. Okay, so a neutron in the nucleus, actually with all this energy, is split. It changes into a proton and an electron. The electron gets out of there, speeds right out. And that energy is what we have as the radiation. And the proton itself is remains inside the nucleus. All right, so that's what B is. A neutron changes into a proton, which remains in the nucleus, and a high-speed electron. The beta particle, which you might see as a little E negative, okay, that's electron symbol, with a 0 on the top, because electrons don't have weight, and a -1 on the bottom, because it's not a proton, it's actually a -1 charge. Or an electron is propelled out of the nucleus at extremely high speed. So it speeds right out of there. And that's actually the radiation. That's what hits you. Okay, beta radiation is about 100 times more penetrating than alpha. It can penetrate 1 to 2 millimeters into solid material, and it can pass through clothing, and it can damage skin. Now, the sun's rays, UV rays, are a very, very weak form of beta radiation. They can't go through clothing, of course, but they can hit your skin, and obviously they do cause cancer, so they can penetrate millimeters into your skin. So that's the form of radiation that is. Gamma radiation, our third form of radiation. It is a very energetic form. We actually cannot even see with our eyes. Obviously, we can't see any of these radiations with our eyes, but it's so energetic that it's more like a light. But it's not the light that you can see. Its speed and its energy is that of light. It does not even consist of particles. The symbol, SYM, it's symbolized by a 0 on the top for its 0 mass, a 0 on the bottom because it doesn't have any charge, and then your gamma symbol. So it doesn't react, we're not going to do any reactions with it because it doesn't change the mass, it doesn't change the number of protons. And that's what makes it really, really dangerous. And this is the kind that they do use in chemo, well, not chemo, chemo's chemicals, but when you're doing chemo and radiation, it's usually gamma radiation that's trying to kill those cancer cells. So they aim it right at wherever the cancer is, and they shoot this radiation to kill all those cells in there. So if we're doing a nuclear reaction, if we have alpha, let's say we start with radium, sorry. So it's number 88 on the periodic table. It weighs 222. Now the mass that I have might not match the periodic table, and that's fine. These are isotopes. Your masses will not match the periodic table. Well, once in a while they might, but they don't have to. The atomic numbers will. Okay, those can't change. Let's say this undergoes alpha radiation. So the first thing I'm going to do with alpha radiation, I'm going to put my alpha particle. Okay? It's always going to come off with alpha radiation. It's always first thing right. I'm like, alpha, okay, we've got that. Now to find what else you have, see this over here, the 88? It's kind of like an equal sign on my yield. Okay? So I have 88 equals 2 plus 86. So 86 plus 2 equals 88. Now for the top number, I have 222 equals 4 plus 218. Okay, so 218 plus 4 equals 222. Okay, so that's where all those numbers come from. I'm just going to erase this so it doesn't get too confusing on you. So 222 equals 4 plus 218, and 88 equals 2 plus 86. So then we look at the periodic table, number 86 is radon, Rn. Do the same thing down here for my beta radiation. Get this out of the way so I get myself a few extra little inches, centimeters there. We've got, let's say we start with carbon. Carbon 14 now. Okay, like I said, the mass on the periodic table isn't going to match this. So it's carbon 14. It gets its name because of its mass, carbon 14. The atomic number is going to be the same on the periodic table, 6, because it is carbon. Now we're going to go beta radiation. So the first thing I'm going to write is my beta particle, 0, -1, E. And then, let's see, I'm adding 0 to my 14. So my top is still going to be 14. 14 plus 0 is 14. Now the bottom, I have a -1 here. I want it to equal 6, so this actually has to be 7. So it's going to be nitrogen. Now this HE you may see written 4, 2, alpha. And this one you may see written 0, -1, beta. Either way is perfectly fine. It does not matter. I tried to go along with what the Pogel did here, so you didn't get too confused. Either way, you'll see it, and it doesn't matter which one. Okay? For your different formulas, mine's right here is written a little differently than the paper you have. I think, let me make sure. Yep, it's written a little bit differently. I gave you a little more space to write this is what it is. So these are the different formulas. Your molecular formula is going to be something that looks like this, H2O2. That's called hydrogen peroxide. But basically, a molecular formula shows the number of atoms of each element indicated by a subscript written after the symbol. Shows the number of each element, of atoms of each element, sorry, of atoms of each element indicated by a subscript after the symbol. Now remember, this part actually is on the top of the next page for you because, well, you needed more room to write. As you can see, there's no way this would have fit on your paper. So on the top of the next page are the different formulas for a molecule, because that's what section 5 is all about, molecules and ions. Because we just dealt with isotopes, now we're looking at ones that don't have different numbers of neutrons. Another one that you might see is if we add hydrogen peroxide, there's this thing called an empirical formula, and that's a reduced version of the molecular formula. So if I have H2O2 and I reduce that, I'm going to have one H and one O. Now the last one, the type of formula is called the structural formula, and that's actually going to show the structure of the molecule. So it shows the bonding pattern within the molecule. So for hydrogen peroxide, this would be the structural formula. And we'll learn how to draw those. Don't worry, we will. But it's going to look like that. Those are the three different types of formulas we're going to be dealing with when we deal with molecules. Now, there are two things that can change in these molecules. Protons cannot. If you change the number of protons, you change the element you're talking about. But the other two, they can change. One will change and it'll become an ion, and we already discussed the other one that's going to change and become an isotope. So we're going to talk about the ion and the isotope. So an ion forms when an atom gains or loses electrons, and it causes these particles to be charged. So an ion is when an atom gains or loses electrons. It causes particles to be charged. It causes charged particles, that makes sense. Charged particles. So it can have one of two charges. It can be positive or it can be negative. Well, the two names we have are cation and anion. When you want to try to remember these, a cation, you think of a cute, cuddly, furry cat. Even if you're not a cat person, go along with this. So you got cute, furry, cuddly cat, and they're so cute and wonderful, and they just make you feel so positive. Okay, so a cation is a positive ion. Positive ion. So it's formed when an atom loses an electron. Formed when an atom loses an electron. And usually, this is metals. Some semi-metals and stuff, but usually it's the metals. So an anion, when you cut up an onion, you cry. It's very sad. It's negative. An anion has a negative charge, so it's a negative ion. A negative ion formed when an atom gains an electron. This is more typical of nonmetals. Remember, electrons are negative. So you get more, you're going to have a negative charge. If you lose one, you're going to have a positive charge. Here's an example, and you might want to Google this picture. The sodium ion is Na, and it's going to become a cation. It's going to be positive, so it's going to want to lose an electron. Chlorine becomes an anion because it wants to gain an electron, become like the noble gases. Now, when sodium actually starts, it's actually going to have, let me make that an actual nucleus here, it has 11 protons in the middle, right? And actually has 3 rings. We'll explain how later, but it's in the 3rd row of the periodic table. So it's 3 rings of electrons. So it's got 8 electrons, or 2 electrons, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. My little dashes are negative signs. That makes some electrons. Only has 1 in the outside ring. It's going to lose that 1 electron, right? Still going to have the 11 protons. But instead of having 3 rings, it's going to lose that electron and lose a whole ring. So you'll see, look at the diameter, right? It changes. It gets smaller. So from the atom to the cation, the actual radius decreases. I'll just put smaller radius in a cation. Whereas the negative one, you're going to be adding them, right? So we have 17 protons here. We still have the same number of rings. It's got 3 rings because they're in the same level. 2, we have 8 around the second one. And we have 7 around the outside one. So it wants to gain 1 more. When it does, it still has 17 protons. But what happens is it's actually going to get bigger because you're going to have more electrons pulling out. And you don't have as many positives pulling them in. And I know this got squished. It's not supposed to get squished down here. It's only because I didn't want to draw on the table. So that's down below. So it's a larger radius for the anion. We're going to get into a lot of that later, but just generally speaking, the cation gets smaller than the atom it comes from, and the anion gets larger than the cation it comes from. So we're going to look at the protons, neutrons, and electrons for these. Oxygen is number 8 on the periodic table, so it has 8 protons. Normally, it would have 8 electrons because these would be equal to an atom. An atom is neutral. But this isn't an atom. This has a -2 charge, so it's an ion. So it has 10 electrons, 2 more negatives. The number of neutrons is just 16 minus 8 is 8. So we're doing this column, the protons, and the neutrons the same way we've been doing. The only thing that's changing in an ion is right here, my electrons. So let's say I have aluminum. It's number 13 on the periodic table. So it has 13 protons. And it has a mass of 26, so 26 minus 13 is 13 neutrons. And the thing that's changing is the electrons. It has a +3 charge. So it has 3 more positives. Well, we already know it has 13 protons, so it has to have 10 electrons. Have 3 more positives than negatives. Let's see, 13 has 3 more positives than 10 negatives. Fluorine's number 9. So it's going to also have 10 electrons and 10 neutrons. You can pause it here and see if you can at least do the last 2 on your own, and then come back and look at the answers. Lead is 82 with 80 electrons and 125 neutrons. And finally, nitrogen is a 7. If it has -3, it's going to have 10 because it needs 3 more negatives. 14 minus 7 got me my 7 neutrons. Very last thing we're going to cover is a thing called isotopes. I told you this is where there's different number of neutrons inside the nucleus, and all the different isotopes actually average together in our world, in our Earth, and that's how we get the atomic mass. So hydrogen is a very, very common one. Carbon's also a common one. But hydrogen has 3 isotopes. Regular hydrogen, something called deuterium, something called tritium. Now you see how there's a little 2 here? That means its mass is 2. So a little 3 here, its mass is 3. Hydrogen, which is sometimes called hydrogen 1, but usually not because it's the most common, has 1 proton, 1 electron, and 0 neutrons. So that's add up to 1. And I already have 1 proton, so I can't have any neutrons. You notice that's 99.98% of the time. That's most of the time. Deuterium is going to have a mass of 2. So we're still going to have 1 and 1 here, so it doesn't have a charge, so it's got to have the same number of protons and electrons. But since there's a mass of 2, 1 neutron has to be in there. And finally, the most rare one is tritium, which has a mass of 3. If 1's a proton, it means we have 2 neutrons. So that's it for 2.1 or 2.4 and 2.5. But before we go, I'm just going to give you, you can see we're missing one on the bottom, but I'm going to give you the names of these polyatomic ions just to make your next homework easier. NH4 is ammonium. And you can look these up if you're not sure how I spelled them. AMMONIUM. The next one is acetate, ACETATE. OH negative is hydroxide. NO3 negative is called nitrate, NITRATE. Then we have bromate, BROMATE. Then we have chlorate, CHLORATE. Then we have carbonate, CARBONATE. Then we have chromate, CHROMATE. And then C2O4 is a little different. It's oxalate, OXALATE. Next one is sulfate, SULFATE, sulfate. Then the last one I have here is phosphate. The last one you have is OCl negative 1, which is hypochlorite. Now these you do have to have memorized, including the charges, including the spellings. So you're going to make a Quizlet on that, I'm sure. If you want to make index cards, that's fine. But you do have to have these memorized. And that's it for this section.